Hi, I'm Jay Gandhi. I'm presenting Lab 6 of Physics 2. So, intro. The purpose of this lab is to observe the interaction between a falling magnet and an aluminum tube. The key principles used were Faraday's law, the B field from the bar magnet, and Maxwell's equations. I used the GlowScript computational model to make my simulation. Brief preview. Due to these principles, a bar magnet in a metal bar or metal tube will stop accelerating. All right, physics ideas. So this equation is like the B field caused by a permanent magnetic dipole um, that we implemented in the computational model. The second equation is Faraday's law, where a change in flux causes an electric field to form. And then this is a derivation. Like the last equation is a derivation to use to calculate the changing flux. All right, visualizing physics principles and assumptions. So, basically, when the magnet enters a tube, eddy currents form above and below the bar. The top, basically current, right, in this little ring, is gonna attract the magnet upwards, while the bottom of it is gonna repel, if that makes sense. So basically the net magnetic force is gonna point upward while gravity points down. So assumptions: we can assume that the only forces that act on the magnet are gravity and magnetic forces. We can ignore air resistance. um, we can assume that magnetic forces equal gravity because it's a constant velocity throughout the thing. Alright, system and surroundings and initial conditions and experiment. The system is a bar magnet. The surroundings are the metal tube because they produce a magnetic force, and then the earth, which produces a force gravity. Initial conditions: I needed to know the length of the tube, the inner radius, the tube thickness, the mass of the magnet, and the magnetic dipole moment, which we found in an earlier lab. Experiment: so we're going to drop the magnet in a tube after finding the north pole of it with zero velocity, then measure the time it takes to exit the tube. So here's my code. These two methods or functions, what they're gonna do is basically just implement the equations, the equations we showed in slide 3, I think, and then this is the bulk of the code. So all this code really does is just gonna iterate through the entire metal tube and find the net magnetic force on the magnet. And then after it does that, it's gonna find the net force, which is just gravity plus the F magnetic. And then it's gonna do a velocity update and a position update on the bar magnet. Similarities and differences and sources of error. So both the experiment and the code show a constant velocity within the tube and a decrease in speed when the magnet enters the tube because of magnetic braking. However, the time it takes the magnet to exit the tube in the code is way more than in IRL. So, sources of error: human error when measuring the time. But I think the real reason is because of a coding error that I made in the simulation. There's probably some small detail. So, what if the resistance in the metal was 0, the current in the metal rings would increase. So the magnetic field it generates increases. This means that the bar magnet would experience a greater braking force. So if holes were cut into the metal tube, the path of the eddy currents is interrupted. So the magnetic force experiences, the magnetic force it experiences is weaker. That was my lab. Hope you enjoyed.